Howdy and welcome to Chapter 2. If you'll recall, the exciting ending of Chapter 1 was we've got to minimize those residuals. And that's going to be a major focus here. Let me remind you, even though for me it was just moments ago that we did Chapter 1. Y sub I equals beta sub 0 plus beta sub 1, x sub I plus residual. Okay, there's your estimated regression equation, all right? You plugged a bunch of data into the computer for, let's do the grade thing again. Grade, hours, okay. So you plugged a bunch of data into the computer, yeah, you can see it, on people's grades and their hours of study, and then the computer spat back in a way that I will now make clear during this chapter, an estimate for beta 1 and beta 0, all right? Now, this part right here is going to be the forecast grade for the student, all right? The grade for the student based on the number of hours they studied and, times this slope coefficient and plus this intercept coefficient. For example, if y equals 25 plus, what did I end up changing it to? I believe 4. I did correct all that, by the way. Let's see. Oh no, I got 5. Plus 5, okay, all right. 5 times x. Then if some student studied for 2 hours, then you would expect them to make a 35. Not very good. Somebody studied for 10 hours, then you would expect them to make a 75, and so on. So these would be your estimates right here that you got from running the regression. And then when you plug the numbers back in, you would see what your regression analysis would suggest this student would have earned had they earned exactly what the regression analysis suggested they did. So that's this part right here. This is what they actually got. So there's always this residual over here, potentially it could be 0, but that's the difference between what your regression equation predicted the student would get and what they actually got. So, let's see here. Let me draw it this way. If, that's where I left you last time, these are all your observations. Each dot represents a student, such that this student I'll make this blue. This student right here studied this many hours and actually earned this grade right here, right? And this student here studied this many hours and actually studied this grade. Well, when the computer is trying to place that line, that regression line, inside those points, it's of course trying to make it to where the points are as close as possible to the line, which is another way of saying, since this is the line and these are the points, hey, let me mark that on here. These are the points and that's the line. All right? So all the points on the line that we're going to have, those are going to be the ones that correspond to that y hat right there. You want the line to be as close to the points as possible, which is the same thing as saying we want that to be as small as possible. All right? We want the gap between each point and the line to be as small as possible. We wouldn't want, oh, it estimated the regression for us and apparently the line's way up here. Well, that makes sense. All the points are down here. It's going to be somewhere in here. You're fitting a line. And again, I know I'm beating this into the ground, but it's so important to what follows. Again, the residual, E, is the gap between the point and the line, and we want that gap to be as small as possible. And in fact, we want the sum of all those gaps to be as small as possible, which is expressed this way. That is the sum of all the residuals. We'd like to, when we add up all the residuals, we'd like them to be that to be as small a number as possible. All right. So that's basically what regression analysis does. But check this out. I done wrote me up a couple of examples here. Uh-oh. Did I walk off? Oh no, here they are. Okay, right here. Yeah. The problem is that we can get a sum of, for example, 0, because we're not going to have a sum of 0 for regressions that don't look much alike at all. And let me give you an example here. What I did was I put together some data here for 2 regressions. One that I'm calling a really good regression and one that I'm calling a crappy regression, okay? Both of them, the residuals sum to 0. But on the really good one, the reason they sum to 0 is because they're all 0. It's because the actual grades and the estimated grades are right on top of each other. Man, in red is what you got from your estimated regression equation, and man, those suckers are nailing exactly what people actually graded. Which would never happen, by the way, because that would mean, but that's an incredible regression, all right? Over here, on this side, the regression equation predicted the first kid would make a 48, and they made a 98. Predicted the next kid would make 100, they made a 45. Predicted the next kid would make a 77, they made an 87. Predicted that the next kid would make an 80, they made a 65. That's a pretty crappy regression, all right? It's way off of what the actual values were. What your regression predicted was in red, and what you actually got was in black. Those are the original data. They add to 0. 50 plus negative 55 plus 10 plus negative 15 turns out to be, oh my God, I've done it again. Sorry about that. Let me fix the math again. All right, well, I'm going to have to go in and change the actual values here to do that. Oh, I can do that real quick. Let's see, so I got plus 60. All right, I want to have a, I'll make that, well, I'll leave that as 80, and then I'll make that a 75. Okay. Like I said, I've been typing for days, taking online exams on how to teach online courses for days, and I apologize there. All right, so what I did was, they didn't sum to 0 before, now it does. So now we've got, plus 60 and minus 60, all right, by changing that one grade down there. So, but the bottom line is still the same. The regression on, let's see, the right is really crappy. Wouldn't it be great? Wouldn't it be great if we had a way to take that into account? Wouldn't it be great if we could show how these numbers actually on the, on your right were actually worse than the ones on the left? How could we show that the numbers on the right are actually worse than the ones on the left? Let me write those numbers down right here. Again, the problem is we know what we want. We want the sum of the residuals, or the sum of the gaps between the regression line and the points, to be as small as possible, right? But unfortunately, we can get, for example, the number 0 for the sum with a really good regression and a really crappy regression, all right? So here were those residuals. RG for really good and crappy for really bad, all right? So we had 0, 0, 0, 0. I only had 4 observations. And the sum of those residuals was equal to, of course, 0, all right? And then on the crappy one, we had 50, negative 55, 10, and negative 5. And that equaled 0. So, if this is going to be our measure of how close the points were to the line, this appears to be every bit as good as this. Well, man, I wish we were in class. I wish I could do this. I like to do this interactively. But you ask the students, and the first place they usually go is here. What could you do to these numbers to make it evident that what's on the right really kind of sucks, all right? What would be kind of, and people say, well, what about absolute value? Well, that's a great idea. Let's do absolute value, all right? So here's a column with absolute value. That's not what we're going to end up doing, but you're thinking the right way. 0, 0, 0, 0 equals 0. Still got 0, right? Over here we got 50, 55, 10, and 5. So now I've got what, 120? Yeah. Whoa! 0 is a lot better than 120. All right, so this indicates that the regression on the right is actually really a crappy regression compared to the one on the left. So yes, if we took the absolute value of each of the residuals, then that would help. All right, that would be like, okay, now I have a way of comparing these two and knowing, actually this didn't work that well, this worked quite well. But what we actually do is square them. All right, and I'll tell you why here in a minute, but let's do the squared values over here. Squared, guess what? I bet you already kind of figured that one out. And then over here, what we've got, let's see here. 5 5s are 25. 125. And I have my phone right here. Let's check that out. I told you in episode 1 that was liable to happen. All right, let's see here. Put in my code. Look for my calculator. All right, and then I want 55 times 55. 3025. Okay, so let's sum those. Let's see, we got 50 and then 5, 6. Is that right? Oh, no, I added that as 1,000. Let's do that again. 125, 3150, 4150, 5150, 5650. Let me double check it. And while I'm doing that, obviously it makes the one on the right look much, much worse than the one on the left. Plus 2500 plus 125. 5650. Yeah, all right. So we end up squaring it, all right? And I know, again, I know I'm beating it into the ground, but it's such an important concept to have down pat before we move on. We are trying to minimize the distance between the regression line that we have estimated and the actual points that we use to estimate that line. And in doing so, unfortunately, we take the sum of that, but if we just take the raw values here, we can come up with 0 for radically different regression lines that are, as a matter of fact, it turns out you can draw a number of different regression lines within the same points and get 0. All right, so that's not going to work. So we need to do something, and an easy way to think about it is we need to do something that's going to make it evident that this regression over here is worse than this one over here. How big was the gap between the point and the line in sum? 120, 0. 5650, 0. All right, so when we use either the red or the green column, we get a better measure of how far off the points the regression line was. Now, we use the squared one because the squared one punishes big outliers, all right? Because obviously, 5 squared is 25. It's not exactly. It's 20 bigger. 55 squared is 3,025. 3,025 is much bigger than the gap between 3,025 and 55 is much larger than the gap between 25 and 5. And econometricians consider that to be a good thing because they say that your regression line ought to be forced to really take into account numbers that are way off of what your line estimated them to be. That a couple of points really close to the line aren't going to make much difference. Some way far away, hey, your regression better be figuring out why is that so far away, right? So you're going to square them all, of course, but the big impact is going to be for the ones that are a long way away, and it's going to force the regression line to adjust to those points because the underlying logic is that if it's that far off the line and there's not some sort of error somewhere, you better be taken into account. This ought to be something you don't ignore because it's a long way away. You should take it into account because it's a long way away. That when you find an unusual situation like that, and again, this is all being done automatically by the computer, but under an unusual situation like that, you need to be taking it into account. And let me see what I have here in my notes. All right, we're on to this page. What we actually do is sum of, and this is the way you would show that. What we actually do is the sum of the squared residuals, which is what we did on the far right over there in green. Unfortunately, I wrote that in red, but I didn't mean to indicate anything by it. Let me read you the fascinating things that John Harvey wrote down here in his notes. What we actually do is the sum of the squared residuals. The reason is that we especially want to punish outliers. It doesn't matter so much if a bunch of observations are slightly off the line, but it does if one is way off. All right, so we want to take that into account. Now, there are other advantages that we went through in my graduate level econometrics classes, but I'm just going to tell you here, all right? He does the same thing in the book. He doesn't want to make you go through and do the proofs. He just tells you, all right? It's easy to use, all right? He has these things listed out in the book. Studeman does. It makes sense theoretically. It makes sense. Like, oh yeah, all right, I can see why. Certainly, you could see logically why you do the absolute value or square to make it something that will be more representative of how closely it fit. And it is the simplest of all regression techniques. In fact, you could use a calculator to do this, and I'm going to do that here as an example in a minute. Just use a calculator to figure out the regression line. The estimated regression line ends up passing exactly through the average value of, write this up here again, y equals beta sub 0 plus beta sub 1 x. Let's see, I'll do it this way. Hat, sub I. Okay, let me scooch out of your way here. And there we go. All right. So there's our regression equation, right, with the estimates right there. Although I used the actual y, so I had to put the residual on at the end. And when you use this squaring of this and minimizing this, all right, when you try to minimize this rather than minimize this or this, when you minimize this, the regression line will pass exactly through the average value for y and the average value for x, and that turns out to be handy in the estimation. The sum of the residuals will still be 0. It will still end up being 0, all right? But it will be a line that is actually more representative of what the underlying relationship was. And last, and he mentions this, it is the best estimator, and he puts best in quotation marks because, God, like I said, we did this painfully in econometrics class, but it is the best linear unbiased estimate. There are a number of, and that means something specific statistically that you don't need to know. So let's just skip by that. There are a number of things that are very useful. Now, how does this work then? How are we going to estimate the line? I'm glad I asked that question. We're very close to doing our first regression, which, if we were doing some sort of therapy, would be a bad thing. We don't want you to regress, we want you to progress. But in this class, we're going to be regressing all semester long. All right. So, how does ordinary least squares work? Well, first of all, don't forget that your residual, I don't think that black pen is as good as the other one, residual is equal to your the actual value minus the value that your estimated regression equation said it was going to be. All right, so there's a difference between the point and the line. All right, the point and the line, the point and the line. And ordinary least squares selects OLS, ordinary least squares. That's what we're going to be doing. That's what we call this technique of minimizing the sum of the squared residuals. Ordinary least squares selects beta sub 0, beta sub 1, beta sub 2, beta sub n, such that is minimized. All right. So what the regression technique does is it selects the betas that will minimize the sum of the squared residuals, all right? So, but it doesn't do it experimentally. I mean, you could think of it, I think it's not a bad way to start thinking about it. Start thinking, well, it just screws around. It just figures out, okay, what if I did this slope? What if I did that slope? And it plays around until it figures out, aha, that's the one that minimizes the squared distance between the line and the points, all right? It actually goes straight to the right answer because it knows the formula. But a good way to start thinking about it is that the computer sits there and experiments and tries, let's try this intercept. That didn't work so well. Let's try it over here. And let's try this slope coefficient and so forth. Hey, that does it. I can't get a better answer than that. When I say better, I mean one that gives me a smaller sum of squared residuals. Now, as it turns out, there's a way to go straight to it. And I'm going to do in a separate video, because I don't want to take up time with it here. Here we go, page 8. You can go through the calculus and figure out, aha, that's why it works, all right? But I'm not going to, it's not part of the class, all right? So I think it's very interesting. I enjoy going over it, but it's not part of the class, so I'm going to skip that here. I'm just going to tell you that if you go through several steps of the calculus and try to you take the first derivative, you set it equal to 0, and you solve, all right? And if you know anything about calculus, then setting it equal to 0 means that the slope of the line is like this. I'm going into it, and I shouldn't be going into it, all right? So, but you are finding the minimum. And so here's the formula, all right? For this equation, it's a little bit more complicated if you get more than one explanatory variable, but let's see. So I'll do it that way. I'll do it this way. Okay. Where does it get these two numbers, all right? Once again, if you set up the original equation, you take the first derivative, then you go through and set it equal to 0 and solve, you end up with this. Solve for what, you might say? Solve for beta hat sub 1. It is equal to the sum x sub I minus x bar times y sub I minus y bar. Right there. Yeah. And then the sum x bar squared. Yeah, that's it. All right. So maybe I'll put this in brackets so that you know that the summation symbol is referring to both of those. Okay. Here's how, and I'm going to do a quick mathematical example. How many observations have I got? I did something with just 5 observations, all right? So we'll go through and figure out and see how this thing works. But you'll never have to do it yourself because the computer does it for you. But you need to see where it got it. You need to feel confident that, oh yeah, this thing does work. This method does work. All right, so this is the solution for beta hat sub 1. You figure out, first of all, an x with a bar over it means the average x. So you've got your list of students' hours of study and students' grades. The very first thing you would do, if you had to do it by hand, was figure out what was the average hours of study, what was the average grade, all right? Then you go through and take student number 1, their grade minus the average, times, I'm sorry, I did that. These are the hours of study. Their hours of study minus the average times their grade minus the average, right? Add that to, because it's the sum of all these individual students, student 2, their number of hours of study minus the average, their grade on the final minus the average, plus student number 3, their grade on the exam minus the average grade, times their, oh man, I did it again, didn't I? Hours, I should jot that down over the top so I don't keep switching back and forth. Hours, grade, hours. Okay, let me start all over. All right, so we're going to take, say, 5 students. And with these 5 students, for student number 1, we take their hours of study minus the average hours of study times their grade minus the average grade, plus, that's what this means, plus student 2, their hours of study minus the average hours of study times their grade minus the average grade, plus student number 3, same thing. In the denominator, and why this works, again, I'll do a separate video on that, but why this works, it does. I'm going to show you, I'm going to prove it to you here in just a second. Divided by student number 1, their hours of study minus the average grade squared, plus student number 2, their hours of study minus the average grade squared, plus student number 3, their hours of study minus the average grade squared. You don't square it at the end. You square each individual difference between what the student earned. How many hours? That's why I wrote that there. How many hours the student studied minus the average for the entire class. So that's how you get beta hat sub 1. And again, I'm going to give an example here in just a second. Beta hat sub 2, remember I told you that with this technique, the regression line, I'll up to 26 minutes, so I think I'll stop at the end of this. The regression line passes right through the average for y and x. So, equal to how did I get that? Check this out. Let's see here. Well, look up here. Just look at the first equation. That's our equation, right? Ignore the residual for a moment because we're just talking about on average here, down here. And on average, what's the residual? It's 0. On average, it's 0. So we're talking about on average down here. And all you're doing is rearranging that equation so you're solving for beta hat sub 0 rather than for y. So what do? You pull the beta hat sub 0, or actually the easiest thing to do would be to take this expression here and pull it over to the left. Let me just do it for you right here. Y is equal to beta hat sub 0. Okay, I told you it's always exactly right for the average. And let's say that we already know this, this, and this, but we don't know this. How do you figure that out? You subtract that, oh, I didn't put a bar over it again, that from both sides. Where's my green pen? There it is. You subtract that from both sides, right? So, and that's all this is, except I have the beta hat sub 0 on the left, which is what we traditionally do, and this part on the right. So, that's what the computer is going to do for a single variable regression. Time check. All right, so I'm going to cut this one here and then start another one where I'm going to give you an example of this so that you can see, prove to yourself that it really does work. Pardon me.